Good afternoon, everyone. Welcome to AP Chemistry. We are going to be talking about reaction mechanisms and rate expressions. So the first thing that we need to know is, well, what is a reaction mechanism? And these reaction mechanisms show a series of intermediate steps that occur when a chemical reaction occurs. So what we're saying is, or what I'm trying to explain is that sometimes chemical reactions don't always happen in just one step. They happen in series of maybe 2 or 3 steps before you have the reactants going to the actual products that are shown in the chemical reaction. A lot of times the intermediate steps aren't shown. These intermediate steps are called elementary reactions. And what we do is we use these rate mechanisms to figure out our rate expressions. In order for us to make sure our reaction mechanisms are agreeable or if they're acceptable, there's 2 requirements. One of those requirements is that the sum of the elementary steps must equal the overall balanced equation for the reaction. And the second requirement is that the mechanism must agree with the experimentally determined rate law. So if we are going to look at this reaction up here where we have NO2 plus our carbon monoxide forms NO plus carbon dioxide. This is going to happen in a series of 2 elementary steps. Now, I just have to apologize ahead of time. My arrows in the next slides aren't matching up. There's a software issue where they're not matching up perfectly. So, the original reaction occurs in 2 elementary steps, A and B. So the first thing we have nitrogen dioxide colliding with another nitrogen dioxide, so it's basically 2 nitrogen dioxides, and that will form an elementary or an intermediate product of NO3. It's hard to see because the arrow is covering up, so let's see if I could just draw the NO3 plus NO, and now the NO, this NO is going to be used in the second elementary reaction as a reactant with carbon monoxide to form nitrogen dioxide and carbon dioxide. So what we do is we're going to cancel out all the intermediate products / reactants. So anything that's the same on the right versus the left side of the equation, we're going to cancel out. So the first thing I can cancel out is this NO3 because I have one on the right side. I also have one on the left side. I can cancel out one of these NO2s because I have one on that side here. And I think we're all done. So let's look at my reactants. I have NO2 as a reactant. I have carbon monoxide as a reactant. Let's look back up at our original equation. Here's my NO2 as my reactant. Here's my carbon monoxide as a reactant. Left over, I have NO, nitrogen monoxide, as a product, and carbon dioxide as a product. So let's look back up here, and there we go. There's our 2 products. So our elementary reactions, the sum of our elementary reactions are equal to our overall chemical reaction. So, how can we determine the rate law? Well, what we do is we can determine rate law from the elementary steps based on what is called molecularity. I know it's a new word. It's not too difficult. Try to use this as much as you can so you get in the habit of using our terminology. Molecularity is the number of species that must collide to perform a reaction, or to produce a reaction. Here we have, and again, sorry, my arrows are all messed up, so the printed ones we're just going to have to ignore. So molecularity, we have a unimolecular, and that's going to be a reaction that involves only one reactant. So your reactant A is going to form your product. So these are going to be your decomposition reactions. Bimolecular reactions are going to be involving the collision of two molecules. So A plus B to form products, or possibly you have A and A bumping into each other, and that's also going to form a product. So that's still considered bimolecular. We have termolecular, and that's going to be really rare. That's going to be the reaction involving the collision of three molecules. So maybe reactant A plus reactant B plus reactant C to form a product, or possibly two A's colliding with one B. Or we have another one where we could do two B's colliding into one A to form product. So the next slide, the rate law for the type of elementary steps that you have. If you have something that's unimolecular, with you only have one reactant, then the rate is going to equal, rate equals K times the concentration of A. Now, if you have something that's bimolecular, which it could be either A plus A, and if you have in that case, your rate is going to equal K times A squared. Now, if it's still bimolecular, but you have two different reactants, like A plus B, then your rate is going to be K times the concentration A times the concentration B. We got a termolecular, which is very uncommon, and again, its rate equals K times A. In this case, it's A to the second power because we have two A's over here. And then another type of termolecular we might have is just K times concentration of A and B and C. So now each of these elementary reactions are going to be deemed either fast or slow. And if they are slow, then they're considered our rate determining step. Rate determining step means that the reaction can't go any faster than the slowest step. So it's like if you're all running as a team, your team will only go as fast as your slowest person. So it's that type of idea. So therefore, the rate determining step, or the slow step, is the one that determines the overall rate of the reaction. So I have this link, and I'm not sure if it's going to work on here, but I don't know. I watched I Love Lucy when I was little. I don't know how many of you still watch it, but it's silly. I watched it all the time. I'm not sure why. I just did. I think my parents turned the TV on and told me to watch TV. So here it goes. Let's see if it's working. My link is not working. Well, this isn't working out very well. So the I Love Lucy rate determining step I wanted to show you was the where Lucy and Ethel are working at a candy factory. But maybe I'll show it to you at the end if I can figure that out. But anyway, what I need you to understand is that the experimental rate law, usually, and that's going to be given to you in most problems, must agree with your rate determining step. Let's try and determine whether or not the suggested mechanisms, the suggested reaction mechanisms, these two steps right here, is an acceptable mechanism for the reaction that we are given and for the rate law that was given. Remember that a reaction mechanism is a series of elementary steps, and it has to satisfy two requirements. The first requirement being that the elementary steps, these two things right here, these two steps right here, let's try that again. This step and this step, the sum of these two steps must be equal to the balance equation given here. That's requirement number 1. And requirement number 2 is that the rate law should match or agree with the experimental rate law. Okay, so the first thing we want to do is to determine if the sum of the elementary steps equal to the coefficients of the balanced equation that was given to us. So what I'm going to do is I'm going to cancel out my intermediate substances, and that would be my N2O here, my N2O right here. That's my first intermediate product, and that product is used as a reactant for the second step, so we can cancel those out. Nothing else can cancel, so I end up with an overall equation of 2H2 plus 2NO forms N2 plus 2H2O. So what I do is I'm going to go back and double check with my original balance equation to see if it matches up. And if it does, we have met our first requirement. The second requirement that we must satisfy in reaction mechanism is to check to see if the rate expression based on the elementary steps are going to agree with the experimental rate expression. I'm going to look at the 3 different elementary steps that were given to me, and from there I should be able to determine which is the rate determining step. The one that's labeled slow is considered my rate determining step. Now if that's the first elementary reaction, then I'm just going to use that one reaction to determine the rate law. But if the rate determining step is either the second or the third elementary step, then I'm going to need to consider all 3 of those reactions when I'm doing rate law. Here are 2 elementary steps. We got the first one, it's labeled slow, second one is labeled fast. So our rate determining step right here is the first one. So like yes, if it's the first one, we only need to deal with that first reaction. And this is what I'm going to do. Rate is going to equal K times the concentration of a hydrogen. So there's just one hydrogen, so we're just going to do H2, times the concentration of NO. And since there's 2 of them, we're going to put it squared. I'm going to double check and see what the experimental had, and this matches up with the experimental. So our rate law agrees with the experimental. Our balanced equation from the elementary steps matches the experimental given. So the reaction mechanism given is going to be acceptable. Okay, so for this reaction right here, for more examples, X plus Y forms M, and that's slow, so this is my rate determining step. And X plus M forms Z, and this is fast reacting. So what we're going to do is let's calculate the balanced equation, and then let's determine the overall rate law for this reaction mechanism. So first thing I want to do is I want to do the balanced equation. So I'm going to cancel out my intermediate steps. I'm going to cancel out my intermediate compounds. So I have, I'm going to do this, 2x plus y forms z. Now, using my rate determining step right there, let's identify what the rate would be. So rate is going to equal K times the concentration of X and the concentration of Y, and that's it. Let's do another one. I'll add. Okay, so same idea. Let's say we have x plus x, and that's going to form m, and we have y plus m, and that will form z. Now this is fast, and this one is slow. So this one is my rate determining step, so that means we're going to have to consider my fast reaction as well. Well, let's do the balanced equation first. So for the stoichiometry, cancel out my intermediate reactants slash products, and I get 2x plus y forms z. Now in this case, since my rate determining step is down here, we're going to need to consider both of these reactions when we consider rate. So rate is going to equal K times the concentration of X, and since there's two of them, we have 1, 2, then it's going to be X to the second power times 1y. Okay, let's see, let's do one more. Hope I'm getting the hang of it. So we have, let's see, y forms m, m plus x forms n, n plus x forms z. This is slow, this is fast, and this is fast. So first steps, let's solve for our balanced equation. Cancel out anything that's similar on the right side of the equation as the left side. Cancel out my m's, and guess what? We're going to have y plus 2x equals z. Now in this case, since this is my rate determining step, all I care about is anything above the red line. I don't care about anything below the red line. So my rate law expression is going to be rate equals K times the concentration of y. Okay, I'm going to go really fast on catalysts since we've already talked about catalysts, but there's a lot of good information that you guys need to read at the end of the chapter regarding catalysts and the homogeneous and heterogeneous catalysts. So make sure you read up on your chapter. But you guys know that catalysts speeds up the rate of reaction by lowering the activation energy. You know that catalysts aren't used up in the reaction. They form an intermediate complex, and then once the reactants bind together, the catalyst is released and can be used again and again and again. Enzymes are biological catalysts. Then there's different types of classifications of catalysts. Heterogeneous catalysts are considered catalysts that are in a different phase than the reactants. So, for example, maybe you have the reactants are gas and your catalyst is a solid. Your homogeneous catalysts mean that the catalyst is in the same phase as the reactants. So here's some examples of heterogeneous catalysts. You're looking at gas reactants with a solid catalysts. So in this case, the gas reactants are adsorbed, and no, this is not a typo. Adsorbs means that the molecules of the reactants are stuck to the surface of the catalyst. They're not absorbed, they just stick. So think of like if you have maybe a piece of metal and all the molecules are sticking on top of that piece of metal. That's the adsorb. And then hydrogenation of unsaturated hydrocarbons is an example. And what we're talking about here is when we are going from a hydrocarbon that has a double bond to a hydrocarbon that's single bonded. Okay. Okay, last slide. Homogeneous catalysts are in the same phase as reactants, and an example would be Freon. Used to be commonly used in refrigerants and aerosol cans. And they're fairly inert, but what happens is the Freon migrates into the upper atmosphere, and when it's up in that upper atmosphere, it's decomposed by high energy light. And in that decomposition, chlorine atoms are released. And those chlorine atoms that are released become the catalysts that break down ozone into O2. And we conclude our PowerPoint on mechanisms. Make sure you read up on the last couple pages of the chapter. We scanned it. We talked about it most in the beginning. So make sure you read up on the end of the chapter. And I will see you tomorrow. Have a good day.